Work? Yes, now it works. So thanks, Rudolf, for the very nice introduction, and which I missed a bit because I have to set up here. So just a moment, bear with me. And now we should be good. Yes, so thanks a lot for the introduction, and thanks to everybody organizing this conference. It's really a pleasure to be here. It's really a pleasure to be part of this ecosystem here that I joined a few years ago already by now. And it's also a pleasure for me to report a bit on the progress that we are making in this quantum computing domain. The talk will be about superconducting qubits. It will be about high coherence superconducting qubits and also enhanced gate operations. And now this does not work. Harry, did I take the wrong one? Okay.
I told you.
Okay, now with the right presenter, it will work. Yes, exactly. I also learned from Harry that one can change the color here, so I choose now a color matching now the color scheme, a blue laser pointer. So thanks. So with this, we're back to quantum computing. So, and before going now into the details about what we are doing here, improving the coherence of qubits and also the quantum gate operations, just as a teaser, what is quantum computing about? Most of you, I guess, have heard about this, but just to bring this back up to stage, what do we want to do actually with a quantum computer? And one can mainly categorize this into different problems, different types, which is one is the simulation of quantum mechanical systems. If you have a chemistry systems and materials systems that you want to study, which behaves according to the laws of quantum, it's best to use some quantum system that you have well under control to study their properties. There is this algebraic algorithms, Shor's algorithm, factorization, mathematical problems that we think, or some of them we know already, can be solved better on a quantum computer. And also more from, because we also heard this yesterday, from the commercial perspective or so, there's lots of interest also in optimizing tasks. Deriving salesman is a paradigm example of what one tries to optimize the route. This just as a teaser in pointing out that what do we need actually for getting this to work. We have to realize a quantum computer with many, and the many means now typically one has about the order of millions of qubits or so. They need to be good, so with high coherence, and we have to be able to control them really well. So we'll need high fidelity gate operations. So where do we stand in this game of getting the first quantum computer to run? Just also a bit from this commercial perspective, also pointing out that there is a huge interest in this field. We know about these companies that have lots of effort in this direction, like Google AI, IBM on the superconducting qubit side. On the ion qubit side, there's the IonQ, AQT startups. There's also now neutral atoms are coming onto the stage rather rapidly. And many of these systems are now in development in the different countries. And also here in Germany, there's lots of effort in building larger scale systems and understanding what is the challenges on the different platforms. Next milestones, we need practical quantum algorithms. We need logical qubits for getting this to work. And so briefly, what has happened here in the domain of superconducting qubits, because I think it also tells us, although it seems that we're still pretty far away from getting a real good quantum computer, it also tells us that we are making good progress. So there has been lots of progress from my feeling in terms of error correction. What can we do actually to correct for errors? I'm just highlighting one of the papers that came out recently from Google, which showed actually that you can increase the distance of the code, so the code size, and get indeed a smaller logical error. It's okay if you look at the numbers, it's really only a bit. So still, if you look at it, what goes into actually implementing this distance 5 codes, because there's many more gate operations, and then I think it's really we are on the right track in getting there, in getting to higher and higher gate fidelities. On the other side, although I haven't looked into very detail into this paper, but just to highlight this, which came out last week, which is on this more NISQ type algorithms. So IBM has now studied a system, a spin system, a 2D Ising chain system on a 127 qubit quantum computer. And what they actually figured out is, even though these qubits are all noisy, one can actually play many tricks. One can play many tricks in terms of error mitigation. And surprisingly, or I'm kind of always surprised if I see that it works rather nicely. And one can then study some observables or expectation values of observables here, so X, Y, Z operators, on a rather large system with up to 127 qubit and gets out meaningful results. There is definitely debates how this now is actually a proof of there is a quantum advantage. I don't want to go into the discussion, but it tells us that we are making large progress actually in this direction. So, what do we have? We have superconducting qubits, and just briefly, what are these qubits that we are interested in? We have electronic circuits, quantized nonlinear superconducting circuits. So what you're seeing here is basically the electrodes, capacitors, a capacitance plate where there is electrons or Cooper pairs basically hopping from one side to the other. In one simple picture, you could just say one Cooper pair sitting on the left and on the right is implementing the qubit state. There's different versions thereof. And it has to go over this Josephson junction, over this weak link, and this tunnel junction actually provides the nonlinearity. And by providing this nonlinearity, we get actually to the situation where we don't have an harmonic oscillator system, but we have an anharmonic system where we can single out the lowest lying energy states as a qubit. So this qubit now is a single one. This goes into a quantum processor. That's one that we are currently using with 3 qubits, here a tunable coupler. This quantum processor, or this qubit chip, then goes into some package. We have to control it. So you're seeing here these microwave lines that are used then to control the qubits. And this qubit then goes into a dilution refrigerator, cooling it down to low temperatures. Why do we like the system? Typical frequencies are in the microwave range, so that's a rather easy control. We have fast gates on the nanosecond time scale, and we can do high fidelity gate operations. And it operates stably, so we can run it basically for days with simple recalibration routines. And we can also scale up fabrication in producing more of these. So how does this then look on a little bit larger scale? So here we see that this dilution cryostat is put on this rack. It's controlled by this microwave electronics here. Here you see the inside of this cryostat again. So here we have the room temperature stage and the different stages in temperature going down to 15 millikelvin. So that's the stage that we are operating in. At this bottom stage, there goes the quantum processor with all the qubits, couplers, control, and readout lines. And this control electronics, then we have to hook up, where we can actually either, as an experimentalist, we like to sit right next to the experiment in a local control, but also there is more and more now going into the cloud, and providing now cloud access is a trendy topic, so that one can basically open the systems up to the larger environment. That's also, as a note at the side, what we did. So we also have now a cloud interface at the WMI. And if everything works nicely, I can also show that it works. So let's see if I find my mouse. So that's what you get. So it's not public, but it's kind of for internal and hopefully soon for other users in this ecosystem. We are using this chip here. So here you see the layout. We are addressing now in this experiment now this qubit 1. And then we can just, as one is used also from Qiskit, just program, load some libraries, load the WMI provider backend, and carry out a simple Rabi experiment. The Rabi experiment is we are applying a microwave tone with a certain amplitude, and then we would like to see these oscillations for driving the qubit to a different state. You see now that the circuit is for the 6 qubits, so we are addressing just one here. We set, now I'm getting nervous, we are setting all the job up, and then we send it to the backend. And now we have to wait a little bit, and if everything goes right, in about 60 seconds or so, we should see now the Rabi oscillations. which we can then retrieve and analyze for data processing. There's also a backup here. If it doesn't work, then you just have to believe me that it works. But I'm confident. So we also worked a lot, and that's kind of also the message behind that, because one has to take care not only about the qubits, but also about the software and about the firmware which goes beyond, because it all should be actually geared toward the direction that we can actually control it in a scalable fashion, and being able also to control these not only locally by experts, but by other people. And, okay. There is a connection. Ah yeah, great. And voila, here we see a Rabi type oscillations, fresh from the cryostat, which shows these nice oscillations. And I could repeat it now, but we would have to wait for a while. And we could also then do simple other type of experiments that would just give us the properties of these qubits. So with this, that's kind of one thing that we are working on, and here would see then some Ramsey fringes. So this is actually nice. So the target audience, I said, is we don't open it for the public as of now, but we are working kind of in improving this and opening this up for students, collaborators, industry collaborators in all of our projects. Could also say it's kind of the first cloud-accessible quantum processor made in Germany. And so that's rather nice. We have to scale up. We have to get solve more of these challenges. What are the challenges? So one is scaling, definitely. So we have to get this under control, that we have many qubits. We have to improve now how can we control these qubits. And then there is topics like, what is the thermal budget that we have? How much heat do we bring into this? How uniform can we produce our qubits? So all this kind of comes as a challenge when scaling up. Then it's definitely also the system, and that's also kind of with this cloud interface, one has to guarantee 24/7, and why we are not saying we open this up to the public, because there's lots of effort going on in actually providing this service, which is then useful at the end. And that goes like characterization, verification, and so on and so forth, which is still challenges. One challenge is also coherence time. So going now back to the basics, what is these qubits? How can we improve now the coherence itself? Can we identify the loss channels and the noise sources? What are these? Can we identify what are these two-level fluctuators and get rid of them? And clearly also in the control and readout, can we optimize these pulses that we are sending in for avoiding some transitions that we don't want to have? Can we do extended gate sets and multi-qubit operations to improve on connectivity? So I will focus on these last 2 points briefly and start now with coherence. So here, if we think about the coherence and dissipation, one thing that comes into my mind, at least as a physicist, is Fermi golden rule. You look at basically what is the decay of some excitation into the, of some atomic system into the ground state. We know kind of that there is two different parts. There's the transition matrix elements, which tells us basically what is the likelihood given a certain perturbation in this Hamiltonian, that it decays from the excited state to the ground state. So that's kind of can be modified in design. We can shape this. The other thing is we have this density of states. And that's kind of all the environment that are operating at the transition frequency of the qubit, where the qubit finds a decay channel into and can dissipate energy, for example, into some atomic tunneling system. The real nature of this is still under debate and still under investigations. It's kind of not very well known what are the exact systems, but we have an understanding that improving on the fabrication, we have to get rid of, we can get rid of these to some degree. So how do we investigate these? So we look at these two-level systems just as a, for a bit better understanding, we model them by this standard tunneling model. So what we're looking in is loss, or basically which is 1 over the quality factor. The standard tunneling model just assumes that we have two positions. So for example, of this atomic system here, which has two positions, which can be to the left and to the right, and it couples, because of its energy spacing, to the circuits elements, to the qubits. We don't want to study first the qubit. So, because we assume not that the main loss channel comes from the electric fields at the interfaces coupling to these two-level systems. So we could study a qubit, but it's harder to fabricate. So what we study first is actually we're using coplanar waveguide resonators. So what you're seeing here is a resonator, which has a certain frequency, and it couples to residues on the surfaces. So what we can do, we measure the S21, so basically a reflection, the properties, doing spectroscopy on this resonator, and looking at the line width. And this line width tells us about the internal losses, tells us about the quality factors, and is a proxy for the qubit lifetimes. That's how a sample looks like in our lab. So we have then not only one resonator, because to improve statistics, we have many of those on a chip at slightly different frequencies, and we can study the Q factors of each of them and getting statistics. So it's on a silicon, so we are doing niobium on a silicon substrate. Typical frequencies are between 4 and 8 gigahertz, and there's also a certain geometry associated to these. Then I also want to highlight, because it's not only a software effort, what I said before, it's only a hardware effort, and there is a particular thing that is typically not very mentioned that often. There's lots of machinery involved in actually getting these things to work. So that's the impression from the clean room that we are having using different tools. And also, it's not only the tools, but it's also the people who does this. So here you see Leon, for example, working on the SCM. You can talk to him then later on if you need more details about that. But it's actually a huge effort in getting this to run and getting a stable process where we can really then operate this qubit at the level of complexity or at the level of quality that we would like to have. Just briefly, what is the deposition and patterning? For those interested, please refer to Leon's poster then afterwards. The essential thing is that we are doing cleaning. We are doing cleaning all the way and using some different acids, sulfuric acids, hydrofluoric acids, for getting rid of organic contaminants or the native oxide layers on these materials. So then we have really a pure, pristine substrate on which we can then deposit niobium in this case. We optimize the temperature, we optimize sputtering parameters, before we then transfer this pattern, this coplanar waveguide, onto the niobium thin film. Here it's also lots of optimization goes in here before we end up then at the pattern substrate, and then we do another cleaning step. And this is actually essential because during these processes we have some residues on there. What does this give us if we just focus on this last cleaning step? We can go now from quality factor, from losses, which is about 1 to the 10 to the minus 6, so a quality factor of 1,000,000 here without post-processing. We can improve that by removing the silicon oxides further, going to 2,000,000 quality factors or 0.5, 10 to the minus 6 loss, and the niobium oxides to about 3,000,000 quality factors or 0.3. It also turns out that the regrowth of the native oxide is not as large as one expects. If you expose it to air, then this regrows. And we're getting now this 3,000,000 quality factors of our resonators. And the best measure, and there is even better versions now around, is 5 or even 10 million that we are measuring currently. So that's kind of, we are optimizing the processes for these resonators. And now we transfer this onto the qubits. And what are we seeing is actually quite encouraging. We are seeing that here from this data points here, we are seeing that we are getting a T1 average, so a relaxation time of 118 microseconds, and a T2s of 300 microseconds. And we're also seeing already qubits that are above this, about 300 to 400 microseconds, and which is quality factors of 10 million for these qubits. And that's actually, so that's this qubit here. And that's kind of state of the art that can be achieved in the field nowadays by improvements on the fabrication. One also has to keep in mind that if you really look at what this means, these numbers, these histograms are actually averaged over time. So we see now that there is a dynamics, in the T1. So that means all of these fluctuators, they are doing some time, they're having some time dynamics. And understanding really what happens there, that's now the next challenge, and then really understanding much better what happens. How does this go in the lifetime chart over the last years? So here we started off in the 2000s or so with nanoseconds of lifetime for the first Kuiper epochs. That's kind of the transmons that we saw. It is 50 to 80 microseconds. Here comes a few other types of qubits. And if you extract, if you don't look into these other types of encoding, so 3D qubits, then we are placing ourselves somewhere here and improving on these lines in this trend. I put here WMI et al., so we are not the only ones, but we are one that can also achieve this, and I'm pretty happy about this. 5 minutes. 5 minutes for this last topic, because we're also studying now, trying to get some physics, so some more interesting stuff done on larger devices. And we're focusing now on multi-qubit operations and extended gate sets. So what is the motivation? The motivation is that if you're looking at these processors, or at least at this one here, then we see that the connectivity is rather low. So it's mostly lines with a few of these qubits connected. And the question one could ask now is actually, can one improve now, for example, operations between this qubit and this qubit by using all of this in between in an efficient way? And so that's what we are doing. We are looking now into a state transfer protocol, or basically a protocol that tells us, can we operate this qubit and this qubit using these as intermediate qubits in between. So the situation is the following. We are starting with this initial qubit, and we want to make a gate between this one and this one. The Hamiltonian is this linearly coupled qubit system. We have the coupling between each of these qubits, these J-type couplings, and each of these qubits gets a frequency. And that's the frequencies here and the couplings in between. If we work out now the effective Hamiltonian, that corresponds then to actually a rotation in the subspace spanned by the n equals 1, so for the first qubit, this one here, and the nth qubit. And one can indeed work out what is this theta, how does it depend on the couplings and on the frequencies, and work out this fractional state transfer Hamiltonian, which has this coupling of this qubit to this qubit, and I'll come briefly back to this later, the parity dependence. In general, it actually turns out that there's pairwise rotation, so it's not only this one and this one, but all pairs basically rotate in their individual subspaces. So then one can work out basically how this state transfer works. We're starting with qubit 1, we are going to qubit 15, we can set the frequencies of the qubits properly and also the couplings, and then we get this state transfer here in theory done. If we want to do this fractionally, so we don't want to implement a full pi rotation, but a pi half rotation, we can do this by setting different coupling constant. And then we get a different pattern. We're seeing we're ending up in the superposition state at the end. It also happens for all mirror symmetric pairs, which is indicated here. Just briefly, it's also nice, because if you're working this Hamiltonian out properly, then you see that this transfer depends on the qubits in between. So now the operation depends now on what is the state of these qubits in between. And maybe let's focus directly on this 3-qubit Hamiltonian, because it's the outline of what we want to achieve. We want to get a gate going between the qubits, and here the 3 qubits is the simplest example. So say we have 1 and 3. The operation that we are getting is a rotation about this axis in this 1-3 subspace, and here it goes in this direction if the state of the qubit 2 is in 0, and because of this parity dependence, if the state of the qubit 2 is now in the excited state, it goes in the opposite direction. So what we achieve with that is actually a controlled I-swap gate. And that's kind of what we are trying to implement in experiment. We studied this in theory and saw that it actually gives us also an improvement in terms of gate time. And that's what we are studying currently. We're having this sample here. There's 3 qubits coupled via tunable couplers. You also see that the T1s on the chip are not as high as I showed you before. That's kind of, we have to do some work on this, also understanding how the different couplings of these qubits on the chip works out. But we see the first nice perfect state transfers. If you're setting the parameters correctly, we see that we are going from qubit 1 to qubit 3 to qubit 1 to qubit 3 and back and forth. and that's these oscillation patterns nicely fitted to a 3-state model, and the decay is basically the T1 decay, so the expected decay. Can also do fractional state transfer, now doing instead of a pi rotation, we are doing a pi 0.6 pi rotation here, and we see that at the specific points in time, at this one here, that the qubit 2 is back to its ground state, whereas qubit 1 and qubit 3 are entangled. So we're getting here already a first indication of this gate that we want to study. And the point is now that we're extending this and also working out the gate mechanism. We're extending the number of qubits. For example, we are studying here the 6-qubit chain here, and see also here that the state transfer works pretty nicely, and want to go on to the next for implementing these multi-qubit gates. With that, I like to finish. I've showed you that we can make high coherence qubits by improvements in the fabrication and the materials choice. We can improve this further, and we are working on that. And we are working on multi-qubit gates, showing that the first fractional state transfer can be demonstrated, and this goes into the direction of enhancing the connectivity of our chips towards multi-qubit gates. There is also some interesting applications, because it turns out that the Hamiltonian that we are having corresponds to fermionic ladder type Hamiltonians, so we can also think about simulating fermionic systems with that. And also, because of this parity dependence, we can also think of schemes how to use this for measuring the parity of some enclosed qubits in using this parity dependence in a protocol. With this, I want to thank you for your attention. I also want to thank all the people involved, and thanks a lot.
Thanks a lot, great talk. I'm particularly happy to see that the first German-made quantum processor is now available to the public. That's very good news. Questions, please. No questions on the talk?
Hi, thank you that was really nice. I particularly liked the last part where you were doing this state transfer. So what happens to these qubits in between? I mean, you said a little bit, but suppose that I want to act, I mean, suppose you don't have 3 qubits but more, and you want to have like qubit, yeah, like this qubit 1 act on qubit n.
Yeah, so that's you kind of see here, I didn't show this. So if you really put now this 1 qubit, so if you have 1 excitation in the system, then it's rather easy. Then this 1 excitation will kind of spread out and then recombine basically in being shared, depending on which type of rotation angle you implement. And it gets rather complicated than if you have this 1 and 8, if you have 2 excitation in the system. I think I don't have a good intuition what happens in between. It's just kind of nested of rotation in all of the subspaces with a specific number of excitation in the system. I think I don't have a good intuition of those, but they return back. Basically, you have to unwind this at the end.
Can you somehow reset, I mean, sort of not reset, but return the qubits to their original state?
That's what you have to, exactly, yes. So you're doing kind of some dynamics in between, and then you have to take care of, basically, you would apply then another rotation of this pair and of this pair and of this pair, so the nested rotation. We looked a little bit whether that, what does this give in terms of efficiency.
Right.
Figured out that it's, okay, it's not, it's a factor that we are finding. It's a factor of 2, factor of 3, 4, 5 or so, depending on the angle that one can gain by this. So it's not exponential, but
sure.
there is something, even if you have to do this back rotations.
Yeah, and then this parity dependence, it's there. So you have to compute that, the parity, or is it the parity of the number of sites, or?
That's basically the number of sandwiched qubits in between. So you kind of, if you could use this, you could indeed use it as a parity check of some 4 qubits in between for error correction. But that's kind of, we have to think about it, how this can realistically be done.
Yeah. Nice that you implemented that, very nice.
Okay, there was a second question, then I think we have to go on.
All right, yeah, thank you for the talk. So you showed that basically the properties of your resonators change slightly depending on whether you're studying them like in isolation or on a chip where you have several of them coupled together, right? And so at some point you have to decide on a particular like patterning on the chip, right? And that depends on the physics or the kind of connectivity you want, but also on these technical aspects like how these resonators actually interact. So can you talk a bit about like how you come to a conclusion and how you strategize on this in choosing sort of a layout of a larger scale chip?
So ideally, and I think that's not a limit at the moment, you can also get this long lifetimes for the qubits on the larger chip. So if you're looking at this 6-qubit chip, it just, at this one here, it just depends a little bit. So here you see these wire bonds, they have to be replaced by more proper ones. Then you have to think about all the geometries and all the crosstalks, for example. And this can be optimized, and I think there is homework for us just to be done here. And then also doing this fabrication optimization in bringing the latest developments from fabrication onto these devices, so there's some time span in between. Still, this will get an issue at some point, and it's not, at least to my understanding, not very well understood what it actually means that you're putting now larger scale, the qubits on a larger scale chip, because you will have many microwave modes that you're coupling to. Whenever you have some line here going, it might well be that this line is coupling to some of the qubits and provide a relaxation channel. And if you're looking now, and there we are at this boundary of millisecond relaxation time, all of these relaxation channels matter at the end. And then you have to be more and more careful basically in designing that. So the answer is kind of, it can be done, I think, to this number of a few hundred microseconds, one should be able, and then I guess it's getting more and more complicated.
And can you understand this through simulation, or is this really experimental work where you just have to try out?
No, you have to do both. You have to numerically simulate, but also the simulations then for these larger 100-qubit chips, they are getting enormously tedious. But it's also now, interestingly, companies are focusing on that and providing also the tools for that. And that kind of helps us then also in getting a better tool and a better understanding.
All right, thank you.
All right. Thank you very much again, and enjoy the beers this evening.
Thanks.
Okay.
Thanks a lot.